All right, so piecewise functions. So click and close. Let me get all your undivided attention up here. Get rid of the earbuds and all that stuff, please. So we've got a piecewise function. How many different pieces are in this piecewise function? Two. Okay, there's two. So remember, what does a piecewise function look like? We've got f of x equals, and then we get the script bracket that's telling us there's more than one behavior here. There can be more than one piece. And then we get one row per piece of the piecewise function. And each row corresponds to the equation that we're graphing and the domain where we're graphing it, right? So what are the steps if we're going to do graphs of this stuff? Because that's my ultimate goal, is I want you to be able to graph piecewise functions, right? And then you can evaluate them too, but that's a lot easier, right? So on the assignment, you're only asked to do two things. Problems 1 through 6 is you're going to evaluate some piecewise functions, but 7 through 11 are the ones where you have to actually make graphs. So let's go through some steps here where we can kind of figure out how we're going to graph these things strategically. First step is let's divide up the XY plane into the domains. So we get a domain for each piece, right? Where a domain is where we're going to graph that piece. So where's the boundary between the domains this time? -1, right? Because -1 is where we're making the transition between the top piece and the bottom piece, right? So the top piece, we're going to make that our blue function. For the blue function, there's the blue domain, right? Okay, what about the bottom, second row? That's going to be our red graph. So where's the domain of that one going to be? When x is greater than -1. And by the way, this is just the line, x equals -1, right? So that's the boundary between the two. So where's the red one going to be? Rod, I'm going to pick on you. You weren't even here, but where's the red one going to be?
Right side.
To the right side of that. There you go.
Oh, crazy.
Okay, so there's the red domain, right? In the blue domain, this is where when x is less than or equal to -1. So to the left of our boundary, this is where we're graphing the line. I know it's a line because it fits the form mx plus b, right? Y equals 3x minus 1. And in the red domain, we're graphing the line y equals -1/2 x minus 5, right? So that's our only goal here. Our only goal is we're going to graph the blue graph in the blue domain and the red graph in the red domain.
I can do that.
You can do that. I think you probably can. So, but to make this a little bit easier, remember we want to carefully choose the places where we're going to get our 2 points. It's not always as convenient. Just quick reminder from yesterday. So normally, if we were just graphing these 2 lines, we would start with the y-intercept and then make a slope triangle, correct? Okay? However, it's not always the best strategy when we've got multiple different domains, right? Because a lot of times the y-intercept is not in the domain where we're graphing the function. So instead, we just want to pick 2 points that are in the blue region. And so to pick those 2 points, we can make a t-table. It's going to be a blue t-table to go with the blue graph in this case. And with the t-table, all we're going to do is we're going to generate ordered pairs. The ordered pairs correspond to the points. It takes 2 points to graph a line, so we need 2 of them. And we're going to pick our x values wisely. If the boundary between the 2 regions is at x equals -1, well, -1, if it works, is a really good value to pick for x, because we want to know where does the blue line end up when we get to the boundary, right? So if I plug -1 into my function up here, what am I going to get back if I'm plugging it in for x? Because that's all I do to find y, is I'm going to plug the value of x into my equation and evaluate to find out what I get for y. So if I plug -1 in, what do I get? -4. I get -3 minus 1 is -4, so we go back. -1, -4. Is this going to be an open or a closed endpoint? It's going to be closed. Good, because the blue domain includes -1. Okay? So there's one point. I guess that point's probably a little overdone, isn't it? But you get it. There's a point there. So, I gotta fix that. That's a little bit too much. There's gonna be another one close to it. There. Okay, so we got a point there. And then we need another one. So let's pick another x value that's in the blue domain. -2. Okay, so if I plug in -2 times 3 is -6, -7. Okay, so I'm going to go from my origin, and here's the origin, right? There's the point with coordinates 0, 0, right? From the origin, we're going to go back 2 and down 7. Okay, and then all I have to do is just connect and extend. And so there's the portion of the blue line that exists in the blue domain, right? Okay, now real quick, let's just kind of think about another approach we could have taken to getting that second point. This was kind of optional to put that second point there. We really could have just used a slope triangle too, couldn't we? Right, because what do we do here? If the slope is 3, I would rise by 3 and run by 1. That's not a great point because it's not in our domain, but we could have reversed those and just gone down by 3 and back by 1. Agreed? To get another point. Okay, so either slope triangle or another point in our t-table. Either way, we got it. That's our blue graph. Now what about the red graph? So for the red graph, we're going to do the same thing. We need 2 points in the red domain. So we could pick -1, right? Because that's on the boundary. Now what's the problem if I pick -1? We can do it, but if I plug -1 in up here, I'm getting a fraction, aren't I? I'm getting -1/2 times -1 is +1/2 minus 5. What's 1/2 minus 5?
4.5.
Yeah, -4.5, right? But that's a little bit inconvenient, right? Because we have a fraction in there. Can you think of an easier value of x I could plug in? 2. How come 2? Okay, because 2 divides into 2 evenly. 1/2 times 2 works out nicely, doesn't it? What's another one? 4 or 6 or 8. Or what's the closest? You're getting even numbers, aren't you? Right, because the denominator is 2. What's the nearest even number to my boundary line at -1?
Well,
0 is right. 0 is right. 0 is even, isn't it? Right? So we could plug in the value 0, which is a really easy one to plug in. If I plug 0 in for x, what do I get? Say it again? I mean, if I plug it in up here, what do I calculate for y, I guess? -5, right? Because that term just goes away. So I get 0, -5, so 0, -5 is right there. And then I could make a slope triangle to get my next one, couldn't I? Right, so my slope triangle would just go, I'm going to rise by -1 and I'm going to run by 2. And there's another point, whoops, there's another point right there. If I wanted to, I could have just put that into the graph, put that into the graph. And I would have used 2, wouldn't I? If I plug in 2, I'd get -1 minus 5 is -6. Either way, I get that point. Right, so once again, this one's kind of optional. I could use a slope triangle. And then all I've got to do now is I'm just going to connect those until I get to my boundary, and then what kind of endpoint do I need? Open. Good, because I'm not including an equal sign, right? And then this is just going to go on forever. And so there's my graph. That's it. That's my piecewise function graph. Now let's write down the domain and the range of this graph. Okay, so here's the other part that just really focus on this. Think hard about this. So when we're writing the domain and the range, we're asking ourselves, think what the domain is. The domain is the set of all of the x values that are on my graph, that exist for my function.
oh,
Okay? So what's it going to be?
real.
All reals. How come, John?
The arrows.
Okay, the arrows go forever, right? Okay, but in order for it to be all reals, that means I don't skip any x values, right? So we can kind of think about this. Let's think about our little ant model here for a second. If the ant is gonna walk from negative infinity to positive infinity on our piecewise function, he's gonna spend some time on the blue graph and some time on the red graph, right? On the blue graph, he can walk all the way up from negative infinity. -1 is gonna be the important number, isn't it? Up to the boundary between the two. At -1, he's standing on that blue point right there, okay? The next microscopic step he takes is gonna drop him down to the red graph, agreed? And he never has to jump over anything. The whole time, he's got some place to stand, agreed? There's no place where there's a hole in the function. If I were to compress this function onto the x-axis to do a projection of this entire piecewise function onto the x-axis, what would it look like? So on the x-axis, the blue part would go all the way from negative infinity up to -1, where I'd have a closed endpoint, right? And then the x values on the red graph would give me an open endpoint right there, and they would go to the right forever. Well, there's no place where there's a gap, right? The red hole is filled in by the blue point, agreed? So that means that the domain is all reals. Okay? Now what about the range? Okay, let's look at the range. So the range is just the set of all the y values that are graphed, right? The outputs of our function. So what about if I project those onto the y-axis, where is going to be, do I have a maximum or a minimum y value?
No. Yeah.
What is it? What is it, right?
Is, -1.
No.
No.
I'm talking about y values now. I'm going to compress these onto the y-axis. Dominic, what's it going to be? -4. Good. That one right there is going to get projected over to there, isn't it? Right? And then all the other infinite points on both the red and the blue, they overlap, are just going to be all the points that extend down to negative infinity, right, on the y-axis. So there's my range right there. My range is just going to be y is less than or equal to -4. Okay? Everybody see that?
That's what I was thinking.
Okay, let's do one more. One more of these. So now we'll do one with 3 pieces. Okay? So let's do same things before. We got a red piece.
Like a tangerine piece.
Well, I don't know if I have tangerine in my color palette there.
It's pretty simple. You don't just do the in-between the whole time.
So we got red, blue, and green. How about it? That was kind of boring, I suppose. But so where are my boundaries going to be between the domains? -5. We got one. So right there. Okay. And then where else? +2. Okay. So let's label these boundaries. So here's my boundary at x equals -5. There's my boundary at x equals 2. So where is the red domain going to be then? Far left. And it just goes forever, right? How about the blue domain?
The middle.
In the middle. And then the green one? There we go. Okay. So let's write down our equations then. Everything when x is less than -5, so to the left of our left boundary, we have the equation y equals what? 2x plus 7. Okay, so the blue equation, so everything in between the left and the right boundaries, we've got the equation y equals what?
X.
No.
No.
What is it? 1. That's it, right? Because there's always 2 parts to each piece. There's going to be the equation part, what y is equal to, and then the domain. Well, that's what y is equal to, 1. So we get y equals 1, and then the green one, y equals -x minus 4. Okay. No big deal, right? All we got to do now is graph the red graph and the red domain, et cetera, all right? So let's make a red t-table. All right, so what's a real good choice for a value of x for the red t-table? negative 5. So if x is negative 5, what is y equal to? Negative 3, right? Because I'm going to get negative 10 plus 7 is negative 3. So we get the point negative 5, negative 3, open or close?
You gotta open it.
Open. There we go. And then now we need another one, right? So what other point could we pick?
You could just do the triangle, man.
I could do a slope triangle. What's my slope for the red graph?
It's 2x.
So what's the slope?
2.
2. So I'm rising by 2 and running by 1. So I could either rise by 2 and run by 1, or I could reverse that and do what? I could go down 2 and left 1 and get a point right there. Or I could, if I wanted to, just go negative 6, negative 5, right? Either way, that's my red piece, right? Okay, the blue one, I don't have to do anything. It's so simple. What's the blue line?
1.
What's the line y equals 1 look like? Horizontal. Good. So I've just got a horizontal line at y equals 1. So it's going to go just right like that. What about my endpoints? Left is, yeah, is it solid or open? Solid, because look, I've got an equal sign. So I'm getting solid, right?
Open. By open, I meant closed.
Okay, there we go.
It's like a door, you know?
Uh-huh, there we go. Open and shut case, I guess, I don't know. So there's our second equation, right? Okay, so the blue line. What about the green one? So the green one, we need a t-table. That one's a little trickier. So what value should we choose? 2. 2. So if I plug 2 in for x, what am I getting? Negative 2 minus 4 is negative 6. Good, so we go over 2 and down 6. 1, 2, 3, 4, 5, 6. Open or close?
Open.
Open. And then slope triangle we can use here. What's my slope?
1 over 1.
Negative 1 over 1, right? Because the slope is negative 1. So I'm going to rise by negative 1. I'm going to run by 1. And I get my second point. And now I can just connect and extend, right? Okay, so there's my graph. Okay, now what about domain and range? So the domain. Now, nobody say it out loud. Everybody just stare at this for a second.
All reals.
Nobody say it out loud.
Oh, hey, that was just a guess. Did I get that right?
I don't know, Nancy, did you get it right? You did.
Yeah, boy.
You got it right. And look, there's no place, every place where we have an open dot, it's filled by a closed dot. Now, what if though, hypothetically, what if that had not been an equal sign right there? What if this had been an open endpoint? It'd be everything but negative 5, right? What would our method of saying that have been? We would have said the domain is just x cannot equal negative 5, right? And what does that imply? Everything's fine except negative 5, not negative 5, right? So that would have been the easiest way to write that down. But for us, this time, that's not what happened.
It's not. It's all reals.
It was all reals. Okay, what about the range? Let's look at the range. Range is a little tougher this time. So let's go ahead and let's project all 3 blue, red, and green onto the y-axis. Yes, sir.
No, I think I got it.
Okay, well, don't say it yet.
I'm not
I
gonna
want to
say
spread
it,
the wealth a little bit. I'm going to give somebody else a chance. So here's the y-axis.
Put that down.
Okay, so somebody tell me, what is the... Okay, I'm waiting. Hey, run. So if I want to project all this stuff onto the y-axis, what is the red projection going to look like? Okay, it's going to start at negative 3 with an open endpoint, right? And it's going to go down forever. Okay, what about the blue? It's just going to be only a single point up here at y equals 1, right? And what about the green? It's already included. It overlaps with the red already, doesn't it? Right? So then this is our entire range. Well, what's that going to look like? I've got the point up here, either y equals 1 or, because I have to pick my pen up to draw the range, don't I? right? I have to draw that point, pick it up, and then draw that interval. So if there's more than one interval, if I have to pick my pen up, it means that I'm gonna have to use an OR statement. So either y equals 1 or y is less than -3, right? And so there's my range. Y equals 1 or y is less than -3. Got it? Okay, there's a lot of stuff going on there, but try it. So here's what I want you to do. On your assignment then, the paper assignment, problems 7 through 11 are graphs. I want you to have, work until you get at least 3 of those done. Okay, and that you can have today to work on that stuff.
7 and 11, 7 to
Yeah.
11.